Hello and welcome to Lab 2, which covers some basic concepts in the C programming language. An outline of what we're going to cover is shown here. I think I'm just going to go ahead and jump in. These slides are available on the website for Lab 2. Alright, so the first topic is representing signals in computer memory in a programming language like C. So this is a slide that we saw last time. I just want to remind everyone that we're working with different kinds of signals. They have different numbers of dimensions. If they're audio, we say they're one-dimensional. They could images are two-dimensional, video is three-dimensional, and then they could also be multi-channel depending on if they're stereo audio, color images, or color video. So let's talk about multidimensional arrays in C, and I want to point out that we use this word dimension in two different ways. So I've been talking about the dimension of a signal back on the previous slide. So we have 1, 2, and 3-dimensional signals. But in C, when we use the word dimension, we're referring to the dimension of the array. And these two things are different, but they're related. In fact, you can see an equation here that shows that the dimension of an array in C needed to store a signal that has a certain number of dimensions and a certain number of channels. The array dimension is either going to be the signal dimension or the signal dimension plus 1 if the number of channels is greater than 1. So for example, a grayscale image will need 2 dimensions, but a color image we will need three array dimensions in C because we have X, Y, and then color. Let's see, and so we see a few examples here. So this is a one-dimensional array, and this shows how we would statically allocate a 40,000 element array that contains 2-byte short integers. Here's a two-dimensional array, so this would be an example of this would be like an audio signal. We're storing the values in floating point type, but it's 40,000 samples long, and there are 2 channels, a left channel and a right channel. This last example on this page, we see an unsigned char being used to store the grayscale intensities in a 100 by 100 pixel image. Moving on, we have some other examples on this page. We have a color image that's, again, 100 by 100 pixels. We have, I don't even know what this would represent, but a 3-dimensional object and even a 4-dimensional object. So I've taken the same table that we saw a few slides back, and I've added another column to show what the array dimension is to hold signals of the different types. And so you see that the array dimension is the signal dimension plus the number of channels if the number of channels is greater than 1. And so that's what we see here. Also, I'm showing down in this other table what the multidimensional array would look like in C. Again, if you were going to statically allocate, this shows what this would look like. And it's important, I guess, to call attention to, if we have a monaural audio signal, this is how we would access the nth sample in that signal. If we had a stereo audio signal, we'd need two indexes because we need to access the sample, and we also need to indicate what channel we're dealing with. For a grayscale image, all we need to know is the pixel element, so it's row and column indexed. If we're talking about a color image, we need row, column, and color, so RGB color. For a grayscale video, we're going to use the frame index first, and then we'll index the row and the column. I want to point out that in MATLAB, the data is stored in a different order. Because the frame index is last in MATLAB, but in C it's going to be first because we want all of the elements of one frame to be stored together in memory. And then here we have an RGB color video. We would store frame first, then row, then column, and then we would use an index to access the color plane that we're dealing with. So let's go through some examples here. So the one-dimensional arrays in C and one-dimensional signals are the easiest because there's an exact correspondence between the samples in the signal and how those samples are laid out in memory. It's just one for one. Then to access the nth sample, we would just say xn, and we could access all the elements in this array, which are the samples in a signal. It gets a little bit more interesting in 2 dimensions. In 2 dimensions, like if we had a grayscale image, in this case the image would be 3 rows by 4 columns, and the way that we want to, of course you can do this in any way that you like, but the standard that I would like to use is that we store matrices or 2-dimensional arrays. We store these in row major order. So in memory, as we move from consecutive elements across consecutive elements in memory, we're stepping across a row. And so again, memory is just a big linear array of elements, and so we would store row 0 first, then row 1, and then row 2, and so on. Accessing elements in the 2-dimensional array could be done using one of 2 approaches. One would be if we had a 2-dimensional array statically allocated, we could use a pair of indices as you see here at the bottom of the page. Or if we literally had laid that array out in memory just using a 1-dimensional array, we would use, so m is our row index, n is the column index, and then to generate a linear index to access elements in this big linear array, we would take m, which is the row index, times the number of columns in the array 4, plus the column index. And that's how we would access elements across here. It's a good exercise to plug numbers into these equations and just check that out, but if you were to do that, you'd find out that you could access, say, the 1, 2 element, or I guess the 1, 1 element here in the array. That's actually the 0, 1, 2, 3, 4, 5th element in the array of bytes, 0, 1, 2, 3, 4, 5. And so that's on row 1 in the array, column 1. So if we have 1 times 4 plus 1, we get 5, and that allows us to access this element here. Okay, moving ahead. Now up to this point, when we've been drawing these pictures of memory elements, every block in the arrays pictured, represented an element. But in real life, memory is actually a big array of bytes. So now in this picture, what I'm showing are the little boxes are now bytes, and so it's just important to remember, we all know this, that if you're storing 1 byte objects, then it takes, you can store 1 element per byte in memory. If we have 2 bytes per element or 4 bytes per element, then of course we're going to take up more memory. I went to Wikipedia and pulled down this table, reformatted it just slightly, but here you can see essentially all the different data types available to us in C. We have chars and unsigned chars, and ints and unsigned ints, shorts, longs, floats, doubles, long doubles, and so on. Let's talk about a model for memory, which introduces the important concept of stack and heap, and this will lead to indexing. So the model of computer memory that we use, we could start with sort of the ideal, that memory is this semi-infinite linear array of bytes. It starts at index 0 and then goes 1, 2, and 3, and so on, all the way out to infinity. Of course, we know that practically it's not infinite, but it's still large. The way that memory operates and interacts with the CPU is that the CPU requests what's at a particular address, and memory responds by returning the value stored at that address. Now, every operating system probably does things a little differently. I don't know. I'm not an expert on operating systems and memory models, but in Linux, this is the model that is used. It's called virtual memory, and it's an abstraction providing each process with the illusion that it has exclusive use of memory. Here a process is a running program. So every process basically gets this virtual address space given to it, and I want to just point out a few things. The executable code and some other things are copied from the executable file into a certain portion of this. This is the low address memory elements. The stack actually appears up at high memory addresses and increases, the stack grows downward. The heap starts low and grows towards increasing addresses, and then in the middle is where the operating system loads code from shared libraries and so on. So for example, if you call printf in C, or something else, fread, fwrite, the code for those things, if it's loaded into this process memory, virtual memory space, it's going to get loaded in here somewhere in the middle. Now, when you are in a C program, say we're inside of the main function, the function called main, where your program begins executing. If you were to instantiate a variable like int n, the memory space for that variable gets pushed onto the stack here. And then as you call functions, the stack grows, and as you allocate additional variables, this stack grows in a downward direction. If you were to allocate an array, that memory is here in the stack. On the other hand, if you were to use the C++ function new, or in C it would be malloc or calloc, the operating system returns a pointer to memory down here in this lower space. So this is called the heap, and it's where you get dynamic memory from, and static memory is all of this up here in the stack. So you might have, for example, a pointer to a floating point value, or an array of floats. The array may actually be stored down here in the heap. The pointer to the array is up here in the stack. The stack is used for anything that's known at runtime or compile time. The heap is used for anything that's not known at those times, so those have to be allocated and deallocated dynamically. And the way that we access and use arrays on the stack and on the heap are a little different. So let's first talk about static allocation on the stack. Let's talk about these different sizes of arrays, 1D, 2D, 3D, and so on, arrays. This shows an example of how we would do static allocation of an array of 40,000 chars. So maybe we could do a define at the top of the program, and then somewhere in the program we would say char x length, and the preprocessor would go ahead and substitute 40,000 in here, and we would then have, as the program is running, an array called x of 40,000 chars. And we could access element 5 and element 4 and 3 as shown here and do math on these things. That's all pretty straightforward. When we get to two-dimensional arrays, again, for the static case, we could define number of rows, number of columns, and we can use this two-dimensional array subscripting declaration, and then we could access elements of a two-dimensional array as follows. So again, this would access the 5th row, 10th column in that array. Now, we could, if we wanted to, and if we wanted to keep track of the details, we could allocate a one-dimensional array and then treat it as if it were a two-dimensional array, or we would basically have to keep track of indexing manually and treat that thing as if it were a two-dimensional array. So this line of code that you see here with some index arithmetic going on is the way that you would mimic the behavior of a two-dimensional array using a one-dimensional allocated array. And as I say here at the bottom, the rightmost subscript varies fastest as elements are accessed in memory. That applies in the two-dimensional case. So the elements that are stored consecutively in memory are the ones that are accessed as we increase and increment the variable, the second variable. So for example, x4 x10 is stored right next to x4, 11. And then x412 is the next one that's stored in memory. x510 is stored some distance away. In fact, how far away is it? Well, it's the number of columns away. Now let's look at the same thing if we're going to do dynamic allocation on the heap. So in this case, I am declaring an integer and setting it equal to 40,000. I'm using calloc here to allocate space for 40,000 floats. I'm casting the return type to a floating point pointer and setting that into this variable x. And once we've done that, now I can treat x as if it were a statically allocated array. In terms of the syntax, of course, we know that it's actually sitting in a different part of memory. We could also access those elements by doing some pointer arithmetic and then dereferencing using the star operator. That does so these things all do the same thing. In the case of dynamic allocation, there's no such thing as two-dimensional dynamic allocated arrays. Everything's one-dimensional. And so in this case, we don't have the luxury that we have here in the static case of using a pair of square brackets to refer to our elements. We have to do it the hard way and keep track of the bookkeeping ourselves. So we have to keep track of the number of columns in the array and then access it in the linear array fashion. Notice that this syntax here would be illegal. The reason it's illegal is because it's a dynamically allocated array. C has no idea how many columns there are, and so you can't do it that way. You have to do it by hand. You have to keep track of all the bookkeeping yourself. Okay, in the three-dimensional case, at the top you see the static allocation. We can just cascade as many of these square bracketed terms as we want to in the declaration and get three-dimensional and four-dimensional arrays and so on. When we go to access the elements, we can just use brackets like we did before to access. In the dynamic case, you can't allocate a three-dimensional array dynamically. You can only allocate space. So we allocate enough elements to hold the full three-dimensional array. Number of frames times number of rows times number of columns. So this would be for a grayscale video. We cannot access the elements using the brackets. We have to just use a single bracket, and we have to do all of the index arithmetic ourselves. So this shows how that might be done. And again, for four-dimensional arrays, I won't go through the details here. This is the static case and the dynamic case. The index arithmetic becomes kind of messy. Still can be done. It could be simplified a little bit. You can save, if you count the number of multiplies required in this way of accessing, there's a few more multiplies than there are doing it this way. So as the number of dimensions increases, the index arithmetic becomes more complicated. Unless the dimensions happen to be powers of 2, then there's some tricks you can play. I'm going to skip over the next couple of slides. What this is talking about here is the opposite of indexing, say, a multidimensional array. See, in the multidimensional case, we know T, what frame we're working with. We also know what row we're working with, what column we're working with, and what channel we're working with. So we know T, M, N, and I, and that allows us to find the index of the element we're after. But what if you have the index of the element you're after, and you want to go backwards and figure out, well, what frame is this? What row? What column? What color? These slides talk about and give some simple algorithms for figuring out how to do the reverse operation. Okay, so next I'm going to transition. In Lab 1, when we were going over some basic MATLAB stuff, we came up with a raw binary file format as a convenience for getting data signals out of media file types into a binary file type that then would be easy to read into C. So let's talk about that here just a little bit. So to process signals in a C program, let's just go through the steps. We're going to transfer signal samples from the input interface. That might be a file or an analog to digital converter. into computer memory. Then we'll format the input samples into a format that's compatible with the operations to be performed. In our case, that's floating point type. That makes things easy for us. And then we do the signal processing, whatever that is. We convert input samples to output samples. Then step 4 here, we format the output samples to be compatible with the output interface. And then we transfer the signals to that interface. That interface might be a file or a digital to analog converter, and so on. Because we want to focus all of our attention on the signal processing in step 3, this is why we've gone to the trouble to use MATLAB as an interface to the outside world. That allows us in our C program to just focus on the algorithms and focus on the operations being performed and not worry so much about data type and whether I've overflowed an unsigned char or an unsigned short or whatever the case may be. We're just going to do our signal processing on floating point values, and we never have to worry about precision. We never have to worry about overflow, underflow, sign changes, anything like that. So this just makes things a lot easier. All right. The header file format that we talked about in Lab 1 is represented as a structure here in a C structure using a typedef. So in our programs, we can refer to this thing called DSP file header, and it's a 5-integer structure. It has the number of dimensions, the number of channels, dimension 0, dimension 1, dimension 2. It's convenience to have this. It's not absolutely required, but it's a convenience, for example, when we're reading in the header, we can read it in all at once by reading in just a single structure, as we'll see here in the next piece of code. So suppose I'm in a C program and I instantiate one of these variables of type DSP file header. That then is a structure of 5 integers. We're going to open an input file using fopen. And then we read in the entire header all at once. It's very easy. We pass the address of the DSP file header. We tell it how many bytes it is in size. So we say size of DSP file header. We say read in one of those objects. That reads in 5 integers from this input source, I, which is the input file. Next, I can calculate the number of samples, the entire number of samples that are needed, or the entire number of samples that are stored in the file. That will be the number of channels times the dimension times the length of dimension 0. Everything is going to have dimension 0. But we won't always have a dimension 1 and a dimension 2. If dimension 1 is equal to 0, then we'll return 1. And if dimension 2 is equal to 0, we'll return 1. Otherwise, we'll return dimension 1 and dimension 2. Okay, so anyway, so you calculate the total number of samples. And then we do a dynamic allocation of an array to hold all the samples in the whole file. Call that X. And then using this a second fread, we read the entire array of samples. The entire file comes into memory all at once using fread. And then we close the file. So we've loaded the whole entire file. This makes it very, very easy. We just do a single fread to read in the header, a simple calculation to calculate how many samples there are. We do a dynamic allocation because now we know how many samples, we know how big the array needs to be, and we read them all in. So now they're all sitting right there in memory. We do the processing, outputting the file. The output data is very similar. So we output a file for open a file for writing. We write out the header. We write out the samples, close the file, free the memory, and we're done. So this is the a set of statements that we could use to interact with these binary files that come at us from MATLAB. We already know how, because we've done Lab 1, we already know how to read and write these binary files in MATLAB. This is some example code that shows how to do that, but we've already done that, so I'll pass on this. I should say, if we were going to read and process a video in a C program, we probably don't want to read the entire video in to memory all at once because video files can get pretty big. You probably don't want to try and allocate that much memory. So usually we process video signals one frame at a time. All right, now we're going to move on to the assignment. I think I will stop the recording and start the assignment in a second recording.